Good morning, everyone. Is your friend here? Hello? Is other friend here? No? I can't hear your voice. Hello? Can you guys hear to my voice?
Yes, miss.
Where is your friends?
You know,
Can anyone please do remind them to come into the class? Only three of you. You want me to proceed or you want me to wait for them? So is everybody here? Can I start my class?
Yep.
So, adakah kita akan kita nak coba? Biasa. Kita jadi orang boleh. Okay, so today we're going to continue our chapter 6, machine instructions. This one is machine instruction part B. Okay, so part A, you can look back at the recordings that I have shared. So as task will be done next week following your tutorials lecturer time arrangement. Okay, for SCSJ, I will do it during our class for lecture next week. Did SCSJ students listen?
Yes,
Hello.
miss.
So next week, as CSJ student, you're going to have your test on Tuesday. Okay? If you are late, no buffer time will be given to you. You need to finish it within the time that you are late. Okay? If you came, our test start at 10, you came at 10:30, it means that you only have 1 hour to be left to do your test. Understand? I don't want to listen any excuses saying that you are late due to the jam or due to anything else. You should prioritize your study before anything else, since you already paid, unless there is some emergency that human can't avoid. Okay? So let's start with our class today. So programming in assembly language, as you all know, it is like your high-level programming, but the practicalities would be different. Okay? So usually progress will be made very tiny step, but the steps usually are non-obvious. So seeing the simple statement in a language like Java may equate to many instructions in assembly language. Okay, all your data manipulation must be performed via register. Therefore, there is no direct manipulation of your data inside your memory. Okay, so you must keep track on which register that being used. No type checking or runtime support. Programmers usually implement using their own data types and check that operation whether they are type compatible or not. Okay? So, this is the instructions for you to remind back. Okay? So, assembly language instruction follows one of the three format. Okay? So, this one we already learned last week also. You have your op name. The first format, op name with operand. The third one would be an op name, operand, and operand. Okay, so these three things will have different formatting. Do you have any question up until here?
No, miss.
So next, where to find the information about your instruction? You can start with the instruction set script sheet. We're available to be downloaded from the platform module website. So this will include description of some but not all about the CDM8 assembly language instructions. So each of your instruction covered in some details, okay, of your platform textbooks. Okay, they will have their own explanation, what do they do, and example of the program that uses them. Okay, so these notes, I think I will share it later through your teams. So how many of you still cannot access the teams yet? Raise your hand. Since there is no response, it means that everyone can does not have any issues to access the teams. So your assignment already uploaded, and the deadline is supposed to be wait a minute. For your test will be done 2 hours next week. Okay, physical during your physical. And then you're going to have your submission of your your lab project 1 on 18th of May, lab project 2 25th of May, group project 1 1st June, group project 2 8 June. So each of the submission need to be present during your class. Okay? Do you have any issues with this one? Is it clear enough?
Yes, miss.
So for lab project 1 and 2, it is the individual based, while group project 1 and group project 2 are group based. For SCSJ student, already set you guys as in pairs. Okay? So usually the presentation will be done during your tutorial sessions. So next, reminder for CDM 8 program. So your CDM assembly language program must start with a sec and finish with N. Okay, these two things are known as pseudo instructions. So what is pseudo instructions? It's actually a command to translate your software. Okay, so where exec will tell the translator where to place your program, while N to tell the translator to stop translating. So in between those two, we would put our machine instructions, okay, data areas, where inside your data areas, you're going to have your data item and also your storage area. So data item, we will use DC, while storage item, we will use DS. So far, do you have any questions?
No.
No, miss.
So next, implementing level 4 structures. So using level 4 machine to solve computing problems requires familiarity between syntax and semantic of the language. Okay, usually you require familiarity of range of techniques to solve common problems. You also need to have your own knowledge and experience how to spot which technique to be used. Okay, while you are using level 3 machine language requires familiarity on different syntax and semantics, but it requires different techniques. However, level 3 and level 4, however, the level 3 program is translated into level 2 program, and there is one-to-one correspond between level 2 and level 3. Okay, so we can see how this will be done to help us to learn in level 3 techniques. So this is the level 4 structures. Okay, you can have two types. One is executable instruction, another one is declaration. Okay, so before we have our executable instructions, we need to have our declaration. So this declaration can be divided into 4 types: constant, variables, data type, and subprogram declarations. Okay, so data type will be separated into 2 parts, which is simple and structured. Okay, so while for executable instruction, you're going to have around 5, okay, expression, assignment statement, selection, interactive, and subprogram calls. Okay, expression, instruction that create your values. Assignment, change the instruction, change your memory. Selection, if, else, select, and so on. Interactive is your while loop, for loop. Subprogram calls is about your procedure, functions, and methods. So I hope all of this you already familiar before we going in depth. So far, do you have any question for this part?
Nope.
No?
No. No.
Okay, so level 4 constant. Permit to use a wide range of different types of literal constant. For example, your integer, floating, truth value, character, and strings. Well, for you to support your declaration of the name, you can put it like below. Okay, constant integer n equal to 5. This is an example on how to declare a constant. Okay, so level 4 variables rely on the use of the name variables. For example, in C++, we declare the specific names for to be used. Okay, so use to point at chunk of your memory that will hold your data item or your data structures of any specific type. For example, if you going to declare int x, y, a, b, c, okay? So you can specify the starting value of your variable. For example, in integer z is equal to 12 or string greeting equal to hello. Okay, so this one is a starting value lah. So if you said your z is equal to 12, so the values that being stored inside your memory is 12, and then when it increment, it will become 13, 14, 15, and so on. Okay? So next, level 4 expression is when we say about expression, it is any symbol that sequence that upon full evaluation that may be replaced by your data item. So the following are are all expression in your C++, huh? Okay? So 5, 10 minus 3, this one is considered as your expression. Okay, so this will be evaluated, replaced by your data items at your runtime. But then take note, none of them say what to do with your data item, whether to store it, to pass it on some sub-program, okay, or be used by others. Huh? Okay, so level 4 assignment statement. So an assignment statement will contain 3 parts. You have your name, assignment, and expression. So execution proceed as follow. First, you need to evaluate your expression on the right. Okay, after your equal. So then you can store the results to your variable name on the left. Okay, so when we talk about left and right, so this would be your value that you want to store. This would be the expression. And this is where you store your value. Okay? So far, do you have any question for this one?
Nope.
Okay, next we proceed. If we say x is equal to 5, it means that we store our integer 5 inside your memory, starting your memory location pointed at by x. Okay, so far, do you have any question for this one?
No.
Then a equal to x plus y. Okay, so this one you need to copy your integers, start at your memory location pointed at by x and y, and then you add the copies together and then you store the results. Same goes with subtraction. If you want to subtract 3 and 10, you need to copy the value first. Only then you perform the subtraction and then you store your value inside the memory that have been pointed by y. Okay? So, level 4 variable declaration. To make this work in C++, must declare the variable x, y, and a before they are being used. Declaring a variable involves telling your compiler about the software that translates your C++ or C or any other language into your machine code. How much the memory to be set aside, and what will be it used for, and what will be the label used to point for it. Okay, so for example, intx, set aside enough memory to inside your memory to store an integer and make the name x point to the first byte of that space. Okay, same goes with your int y and int a. Okay, so next, if we want a single byte constant in platform 3 program, for example, the number 5 or the character h, so we need to include it as an immediate operand of LDI instructions. Do you remember your LDI and LD? So LDI is stand for load immediately, while LD it means by load. So usually we will have our load, only then we have our LDI. Okay? Or it is in a reverse way. Which one? SCSJ? We have LDI first or we have LD first? Okay, since you guys doesn't want to communicate, it's okay. I will read the slides. Okay, so we may use a label and a DC pseudo instructions to declare a name constant that will be held inside your specific memory. So this will be available for use as many times as we want if we don't store a different data item that through that memory cell. So we'll need two instructions to load the constant into your register, which is an LDI followed by an LD. Okay, so CDM 8 platform tree constant. If we want to use a multi-byte constant, we must use a DC to start it, to mark its start address. For example, hello, string hello. So a multi-byte value cannot be loaded into a single register and takes many more instructions to process. As well as marking the start address, we need some means of determining when we have reached the last byte of your data item. For instance, the case of a text string, we will place a null character in the text byte after the last character in the text string represented by all zeros bit pattern. So for example, this one, we use the LDI to load the literal constant into your register. So load immediately 5 into your R1. Okay, load immediately your value 10 into R2. So note that nothing is done with the value since they are left inside your register only. Okay, so name your constant. So we may place the constant inside your memory, inside your data area. Okay, and give those memory location labels or name. Okay, so for example, DC5 in your A, DC10 inside your B. Okay, so this constant cannot be used until they are loaded into your register. Okay, so constant can be loaded into register from the name location. For example, we have our A, DC5, B, DC10, T, DC3. Okay, so we load A into your R0, and then we load the value from R0 into R1. Okay, so we load immediately the value of B into R0, and we load the R0 value into R2. Okay, so all of this will keep on repeating. That's why they said load immediately first, only then we have load after that. Okay, so still we do nothing with the value because we are just loading into the register. Okay, so declaring a multi-byte constant. Okay, so a single DC may be used to declare an ordered collection of your constant, which programmer may treat as a multi-byte constant if she or he wishes. Okay, so you can declare it like this. Okay, and then indexing a multi-byte item, we have seen how to declare a name multi-byte constant, right? So the name is the address of the first byte of your data item. So how do we get this address of subsequent bytes? Usually we will use addition. Okay, in the example on the previous slide, the name greeting. So the address of the cell, memory cell containing hash. Okay, so the greeting plus 1, the address will be having E. Greeting plus 2 is going to have your L. Okay, so does you see the similarities with the string and list inside your Python? So when we load the address greeting into your register to point the whole string and add the index to it, add the pointer to a specific character. So far, do you have any question for this part?
No, miss.
Okay, so next, CDM expressions. Okay, CDM expression does not provide facilities to write an expression like this. Okay, not directly, but we must write the sequence of instruction that produce the data item obtained by evaluating the expressions. The resulting data item or its address must end up in your register so that we can do something with that. Okay, so the data item that make up the expression must come from somewhere, and there are only two sources that we can use. The first one, the platform register and its memory cell. And the second one is the number of register that it takes, how much loading and storing that we must do along the way when we evaluating our expressions. So next, we use our LDI to load the constant into register, then perform arithmetics. Okay, so this will be the sample. And your results, once you perform the subtraction, your result will not be done anything because you just left it inside your register. You did not give any extra instructions. Okay, so this would be the revised example. So we may place our constant inside your memory in your data area and work on them. Okay, but then still we does not provide anything with our results. Okay, so as I mentioned, a sec would tell you where you start your what do a sec do, guys? What does the ASEC do? Did I teaching a human or just doing a recording, guys? Okay, fine. So next, using variables in expression one. So a program variable is actually a collection of memory cells that may contain different bit string at different time during program execution. Any memory cell may be treated as a variable. However, this is potentially dangerous. So some memory cell contain your program instruction. Some of them will contain data item that intended to be kept constant. For example, number of letters inside your English alphabet. And then you're going to have your content of this cell should not be modified at your runtime. Okay? And then to maintain discipline, we introduce the notion of reserved memory cell that may be used as variables. Okay, the CDM8 assembly language provides us with pseudo instruction that can be used to declare your storage, for example, using the DS. Okay, so reserve 1 byte chunk of your memory named as P and second byte chunk as a memory named Q. Okay, so this would be an example. So do you think this one is okay? Still don't have answer. Okay. So next, so what are the variables used for? The first one is the whole point of reserving memory cells to provide your storage space for your data item that have been calculated. Okay. So it will be an input to the program at the some point of your execution. So this memory cell may be used to store your results or temporary storage for your data item that we cannot accommodate in your register because we do not have enough of them. Or it can be as a storage of your data item that have been provided by the users, or it also can be data storage of your data item from another programs or platform. In fact, we use reserve memory cell to hold on to your data item that we want to use or keep later on. Okay, so why name your variables? We name our variables due to we want to avoid to having this use of addresses of the memory cell that we have reserved. So the name is converted to the addresses of the first memory cell in the chunk that we have requested to be reserved. Okay, usually we will use our arithmetic operation on that address to obtain the addresses and contents of subsequent memory cell. Okay, so aside CDM translation software support the use of limited address arithmetic in assembly program. So for example, you can see below down there. So do you have any issues to understand this? Anyone can explain what does this code do? Anyone can explain what does this code do? Hello? If anyone can explain what is going on with this code? Is anyone here? Hello? Is everyone here?
Yes, miss.
Why no one respond to me when I ask questions? I'm asking, what does this code do? Still have no response. I'm asking, what does this code do? So let's have a 5-minute break. Okay, so let's proceed. Assignment. This is a simple assignment. Okay. For a simple assignment, we'll assign value 5 to your variable name x. Okay, so this would be the example of how you use the code. Okay, in actual fact, what we are doing is storing the value 5 to the memory location with address x. Okay, so the hashtag, after hashtags, the term is meaning to explain the words here. Okay, so this is also the examples. Okay, next, this is the assignment that where you want to perform the addition of x and y. So now, create and test a whole program. We have the instruction to implement the assignment statement, but we need to wrap the whole lot up to the CDM platform 3 program and test it. So what we are implementing is memory A is equivalent to memory X plus memory Y. So this is quite straightforward to test. So repeat the sequence several times. So run a new pair of your number in your memory location X and Y. Run your program. Check the corrected result stored in the memory location A. Okay. So why do we need to use your GC for X and Y? Because it helps us to test our program. To test that the assignment statement works as it needs to have values stored in location X and Y. At this stage, we want to avoid the complexity of dealing with input from outside the world, for example, your keyboard. Okay, we place our values at the location X and Y for testing purposes. To test your assignment statement, we will compile and run the completed program for a series of pairs of example values placed inside your location X and Y. So, developing a program, first you need to create a scaffolding. You need to mention exec, start from where, and then you do your executable code. You put a halt, and then you have your constant and variable declaration, and then you have your end. So this will be the format. Okay, so every CDM assembly code program we ask you to write will include this scaffolding. Okay, so exec will tell the compiler to store your program at location 0x00. Halt instruction that will be translated and passed to the platform 2 and will tell your compiler to stop translating. So develop a program, declare the simulated input X and Y with the variable A. Okay, so this one. Next, you will load the two input into your register. And then you will add up those two values together. This one, after you add up, you get your results and you store your results. So this is the full code of your results. So far, do you have any question for this part? Still have no response. Okay, good. So, testing the program, compile and run it. The value of 6 and 8 will be placed inside your memory cell X and Y. Check whether you get the 14 inside your memory cell R or not. Then we'll place different value in your memory cell X and Y and compile again. Choose the new value that result should be different. So no good having another pair of result that add up to 14. So run the program and check the correct value end up in a cell memory A. So do this several times with different pairs of values. So this will be the code that you shall need to run by yourself. And then debugging the program. So what if the result of your test is incorrect? So you need to perform a debugging due to there is a bug. So how do you find a bug and how do you fix it? So these six would be some of the factors causing the bugs. First, you are misunderstanding what it was required. You are using the incorrect algorithms. You use the wrong choices of operation and operand. Misunderstanding what the instruction does and incorrect sequencing of your instructions. Okay, so before you debug, the first step of your debugging, you start with your algorithm. Do the dash checking to ensure it gives the right result. Assuming it does, check the implementation. Work out how was each step inside your algorithm is meant to change the platform. Step through the program in one instructions at a time, checking, and that is thus what the algorithm say it should do. Keep stepping until the change you see in different from the one that you expected. There is an error in or before the instruction you will have execute, work backwards from where you notice the error is. So far, do you have any question for this one? Do you have anything you want to ask?
No, miss.
So, this is some common errors. Forgetting to load the right address in your register before trying to load the or store a value from or to your memory. Getting the operand in the wrong way around. Okay, and leaving your collecting your result in or from the wrong register. So reading your LD or ST as if they are moved your instructions. So far, do you have any question for this part? So now, I want all of you to try. Run this code. Still remember where did I mention you need to run the assembly language code?
No, miss.
Why no? I thought all of you don't have any questions previously. You should run your Coco IDE. Where is your Coco IDE? Have you guys installed your Coco IDE?
I haven't yet.
I thought I already give the folder so many times ago.
I don't know why mine I unable to download.
So it means that you guys does not take note whatever I said previously. I asked you to install your things and you did not install. Okay, good. I take note about this. Anyone that have installed Coco IDE? Raise your hand. I have provided you the software. None of you download and install inside your computer. Oh, it's good.
Miss, about like the MacBook, I can't install it.
You can't install it. I already provide you along with the software manual, right? Did you receive that?
Yeah, miss. I tried like the last time that we did it, and I told you that I still couldn't like download it, so you will
Did you
ask the
follow
new
step by
page.
step?
Yes, miss.
Try to do it again. If cannot, you have to ask from your friends already. How about others? You need to use this software for your assignment. So it means that nobody takes seriously what I'm telling you. It's good. It's good enough. By hook or by crook, I want it to be run now. Is anybody here?
Yes, miss.
Yes.
Can you run this one? So it means that nobody ever tried to download and ever tried to run the system. SSJ student? SCSJ student?
Yes.
None of you install this one, even though I asked you to do it in the class, except for Nishimura.
No, for me, I couldn't. I don't know. My laptop couldn't download the like even Logism as well. I couldn't download it.
Others?
For me, I find out I have it on my laptop.
Then?
I've never
Did you
used
try
it.
to run the program?
No, never.
You guys in degree level, eh? Not everything I should mention to you and you should do it. You have to do it by yourself. Other center students? KL? Penang? Any of you try already about the Coco IDE? SCKL? Are you here?
Yes, miss.
Have you run the Coco IDE? Did you try?
I'm getting errors, miss.
What error? Can you show me your errors? SCKL, just now who respond to me saying that you have issues? Share your screen. I want to see it. Suppose you be able to run. So tutorial that I give you previously, no one do it lah. Okay. Since you guys are so clever, I don't think I need to show you this thing again. So you can do it by yourself. Okay. So let's proceed. So next, working with n-byte numbers. So CDM8 is designed to perform arithmetic on numbers representing 8-bit strings, but the number range that available if we use 8-bit string is very small, where we have 0 until 255, which is unsigned, -128 until +127 for the two complements. Many real-world data values fall outside what can be represented using your 8-bit string. So we need to be able to handle the numbers that are represented longer than your bit string. For example, a 16-bit numbers are represented by 2 bytes stored and process each other. So byte ordering, if your numerical value is represented in sequence of 2 or more bytes, we must decide in which order the bytes should be stored in your memory. So we have two types. One is big endian and another one is little endian. So big endian is an order which your big N is stored first, while little endian where an order which the little n will be stored first. So the terms for big endian and little endian came from Jonathan Swift novels, Gulliver Travels. So the ordering of your bytes in multi-byte data item has major implication for your processing. Okay, so this will be the example where your decimal number 20306 can be represented as your 16-bit unsigned binary numbers. When we convert into unsigned binary numbers, it will have the 4F52. Okay, so this will be stored in your memory as two successive bytes. So one would be the big endian, another one is your little endian, where you will split them into two parts. Okay, so when you sit into two parts, you need to check you are using big endian or little endian. If you are using big endian, you will have your high byte first, only then you go for your low byte. Okay, which is your 4F, and then you go for your 52. But when you go for little endian, you're going to have your low byte, only then you have your high bytes. Okay? So next, representing 2 bytes numbers. So representation of 20306 is as the bit string would be 0100 1111 0101 0010. So this one, how do we get this? Is the conversion from this one into this. How do we convert? You have to dig it out by yourself, since this one already teach you in previous chapters, in the early of the chapters. Okay, so the big endian, we will start with exact 0x10. Okay, so you will start with 01001111. So we will take the high endian first. The high bytes, only then we check for the lower byte. While for little endian, it will be reversed. You will doing the small byte, the low byte, only then we go for the high byte. Okay? So this is how does it looks like when we put them in the tables. Okay? So next, the addition, suppose we want to add two numbers, 2 byte numbers, but we only have one machine that can be add up two 1 byte numbers together. So how can we do it? So a 2 byte number usually does not fit into 1 byte hardware box. So how do we do it? Let's see. So the solution would be you will split them into two numbers into two 1 byte chunk and add the corresponding bytes together. Okay, just like this one, low and low, high and high. So you will separate them into two components like this and add them up together. Okay, at the end, once you have your values, you will combine them back together as your hardware A plus B. Okay, so this would work, but how? How about the carry out? So the carry out from low, has to be added to the high, and the carry out from the high will be carried out for the whole sum. Okay, so this will have your carry flag. So this is where the carry out from the most significant bit of your result is held in the future. So it will modify each time a new ALU operation is performed. Okay, so we need two kinds of addition. So simple addition and add with carry in. Okay, so when we talk about simple addition, we just simply add two numbers of two hardware length bit string together and produce a sum and a carry out. So which can be used as a carry in to the next ALU operation. Okay, and the second one, we will have add with carry in. Okay, so the two instruction would be different. So simple addition, we only have your ADD. While if you have the addition with the carry in, you put your ADDC instruction. Okay, where you add together two hardware length bit string and plus with the carry out from the previous operation, which you will use it as your carry in and produce your carry out. Okay, so far do you have any question for this one? No? So next we proceed. The carry flag in the bit slice addition. So for the second kind of the addition at C, to work, we need to hang on the carry out from the add operation that was applied to the lower bytes of the two numbers. Okay, use this as carry in when you're using the add C to add together the high order bytes of the two numbers. Okay, so the carry flag is used for this purpose where it will update it every time your ALU operation is performed. It is left unchanged by your memory operation so that we can store the low order byte of the result without affecting your carry flag we want to use when adding them together. Okay, so this would be the steps by step when you use the bit slice addition. Okay, so next, this is the example of the assembly code when you perform your bit slice addition. This is the continuation. So this will be the full code. Okay, so same instruction sequence for both. So the procedure for adding two byte numbers together in the same or no matter whether they are stored in the memory or in Big Indian or Little Indian order. So what changes is the addresses of the memory cell that you use to hold each of the two bytes making up a number. Because we have label of each of the memory cell correctly and then referred them by their own labels. Okay, so this code will work no matter whether the numbers are represented in Big Endian or Little Endian. Okay. So how about your shift? So we say a number could be multiplied by using 2 shift left and divided by 2, but divided the 2 using a shift right. But what if the number occupies a longer bit string that the hardware support? Okay, once again, we can use the bit slicing to solve your problem. And once again, we need two different kinds of operations. Okay, so shift, we want to shift 2 byte numbers, one place to left, but we only have one machine that can handle 1 byte numbers. Once again, the 2 byte numbers does not fit into 1 byte hardware box. So that's why we are slicing them into 2. So the arithmetic shift left fill with a 0 at the right hand end of your bit string and create a carry out at the end at the left hand end. So the most significant bit of your original bit string. This is the overall effect that we want for our 2 byte bit string. But if we use the arithmetic shift left operation on both bytes, it's not what we'll get. So we need a slash left shift operation to use on the high bytes. Okay, instead of shifting 0 in the right hand end, it shifts in the contents of your C flag from the last operation. Okay, so this is the steps how you do it. Okay, so if we have 2 byte numbers but only have 1 byte hardware, we bit slice the arithmetic shift to the left. Okay, so the first step, you put low X into your hardware A, and then you use the arithmetic shift on your A, where the shifting into in 0 at the right hand end of A. So hang on your carry out C from the result to the shift key, save your result as low, and then put your high X into your hardware A, use the slide shift left to shift C into the right hand end of A, and then you save your result to your high. Okay, so this will be the example of the codes. Okay, so far, do you have any question for the addition and multiplication? Okay, don't have. So let's proceed. So shifting to the right, which means that you're dividing by 2. So arithmetic shift right fills in a copy of the sign bit at the end of your left hand end of a bit string and a bit drop of the right hand end, at least the least of significant bit of the original bit string. Thus, this will overall affect our what we want from our 2-byte bit string. But if you use the arithmetic shift right operation on both bytes, it's not what we'll get. So we need to perform a slice shift right operation to use on a low byte. Instead of shifting the most significant bit in your left hand and it shift in the bit that falls off from your high bytes. So this will be the step for arithmetic shift right using your bit slicing. Okay. So this is the code. So negation and subtraction. To negate a number that we find its two complements, so the simplest way is we flip all the bits and add one. But how do we do it? First, we use our bitwise NOT operation where it will flip all your bits on the whole number. So that we add the 1 to the result and we have our negated of your original number. If we can negate our y, we can calculate x minus y by adding negative x to your negative y to your x. Okay. So bitwise NOT is each bit in your bit string is treated as if it were a true table. So 1 is true, 0 is false. So a bitwise NOT converts all trues to false and all false to true. Okay, it means that 1 to 0 and 0 to 1. In reality, what happens is that every 1 in the original bit string is replaced by a 0 in the result, and every 1 value will be replaced as your 0. So in other words, we flip them all. Okay, or we reverse it. So this is the code for negation. Okay, this is the full code of bit slice negation. Subtraction with bit slice, we said that two complement give a subtraction for free. But what are the subtraction performed on your numbers that are held in your bit string too long for your hardware? So bit string came up to the rescue, but we must remember to do it for each of the operation x minus y is calculated as below. So first perform the bitwise negation of your y, where you will produce a negative y, and then perform the bitwise addition of y and negative y. That's all for chapter 6. Is there any question for chapter 6b? So we don't have any questions, eh? Okay, so we don't have any questions. Let's continue. So let's do some recap. So provide me the answer for each of this, screenshot and submit later. Done. Okay, next. So CDM8 instruction, how many formats? Explain briefly all of it and provide an example for each of it. Okay, so these two things I want you to submit by today before 2 through Teams. Okay, chapter 7 is about logic structure using your macro. Okay, so this is your control structures where consists of your looping and branching. So looping is about for, nested for, while, and do while. Okay, so decision control can be divided into two parts: conditional branching and unconditional branching. If else, if, and also your switch. So far, do you have any questions for these two?
Wait, miss. The work before that, can you show again?
I thought you guys already screenshot.
Nope.
Hurry up.
Okay, done.
This one?
Done.
So selection, there are situations that we need a program to select one of two courses for your action. Okay, for example, we have our condition. In your Python version, we have if, and then you put your condition, and then you put your statement, and then you have your else statement, right? So only one that you can choose to be performed. So which one depends on the value stored in the memory labeled as first and second. Okay, so how this can be achieved inside your assembler? First, you need to perform the loading first. So load your bit string from two name memory location into your two register, and then you compare your contents of your register to see which of the two contains the greater numbers. Okay, store the greater of the two numbers into your memory, so maximum of the two original numbers. So the program needs to choose which one is to be stored. So it does this by choosing one out of two different instruction sequence to be executed. So this would be the example of the full code. Okay. So at here, if you see that CMP is about compare, move is moving the value. Okay. Max is the max value. Okay. So developing a program, as you already know and don't have question just now, okay, you need to have your scaffolding. Okay, only then you can put your executable code and then you put your constant and variable declaration. Okay, so declare the first, second, and maximum code first, only then you perform the execution part. So this would be the half of the code. Okay, so this one, just now we have our declaration, we have store our value, load the value inside your first and second, and then we have to do the comparison, load the value for maximum and store it. So general principles of I and if with an if. Okay, so it is implemented in level 3 using branch instruction for these two things. Okay, so if, without, and else. Okay, so if just a single if, we just only have if and a statement. If we have if and else, we have if, the statement, and else and their statement. Okay, so a structure of this kind between execution and non-execution of the sequence instruction. So this function may be implemented using your conditional branch. If your condition is met, PC is modified. So what is PC? Your program counter. Okay, to take the processor around the instruction sequence that follow on your sequentially, where is it from? If the condition does not meet, execution continuous sequentially. Okay, so they would not have any stop loop. Okay, so while else, so we expected an assembly code to be more complicated, therefore we need two branch of your instruction. One is conditional, another one is non-conditional. Okay, but we doesn't want to use the branches. So branch are hard to be used and can only made to work effectively if we litter our program with labels, which hamper your readability. In order to improve the readability and avoid the use of branches, we introduce the if and fee constructs, if, else, fee construct. So if fee construct is used when to choose whether or not to execute a sequence of instruction, while the second one is used to when you want to choose between two instruction processes. Okay, so this one is fee and is if and fee, and another one is if else fee. So if and fee is used when we want to choose whether the execution or sequence of your instructions. If, and then you put your instruction to set up your flags. Is condition is execute the instruction sequence. Fee is to continue the rest of your program. While is else if else fee is used when you want to choose between two instruction sequence. If instructions to set up your flags is condition your first instruction sequence, else you have your instruction sequence 2, and fee would be continuing the rest of your program. Okay, so these are not strictly speaking through your level 2 level 3 language construct, because they does not map to a single level 2 instruction. Therefore, they were implemented using your macros. So a macro is actually a sequence of instruction. They may be inserted into your program when referred to by name. So we have a CDM macro assembler that does this for us. So this one will be known in your platform 3.5. Okay, but we would not dwell on how this work here. This one you can find inside your platform textbooks. Okay, so how was this 3 half level difference from your level 4? In Python, we might write if condition, and then we have our instruction sequence, right? Where your number in R0 is greater than number in R1, the indented instruction will be executed. So when your number in your R0 is less than or equal to the number, nothing will happen. Okay, so in this all very well, but assembly language, we do not have the instructions that's the same job as the less than or bigger than. So we need to do the two-step implementation. So two-step implementation is like you subtract your R0 from R1 from R0 and then check whether they have the result subtraction was greater than 0 or not. If yes, okay, so the instruction sequence will be executed or else it will be skipped. So far, do you have any question for this one? Do you have any question for this one? So let's have a 10 minutes break before we proceed. Okay, so far, do you have any question for today's topic? Still have no response, so I shall end our class here. So you figure out how for you to download your Coco IDE, since the Coco IDE is required for you to do for your group project and lab project. I don't know how, but you have to use it for your group project and lab project. Okay, so I end our class by today. For today, so SCSJ, see you tomorrow, and please do not be late. Thank you.
Thank you, Miss. Sorry, Miss.
Thank you, Miss.
Thank you.
Tahu tak Maria masuk kelas saya pukul berapa?
Thank you, Miss.